Let's see. Just be on the safe side. Just pull one out of here.
So you just treat it the same.
It's around.
Yeah, you usually go the same way with the X squared in there.
Yeah. That one's interesting. This one's kind of interesting, actually.
This one's so much better, I think.
Okay. So let's see.
Assume, yeah, summation from n equals 0 to infinity, Cn, x to the n.
Yeah, so this is about the ordinary point 0. What would be a non-ordinary point, a singular point?
X equals 1.
1. I like it because it would make this middle px, it would make this non-analytic, meaning there would be a power series. Fine there because it's not even defining. I like it.
So, hypothetically speaking, if you were to ask us to solve it about x equals 1, then we would say we can't.
Yeah, that would be really evil.
Or just
But yeah,
like,
because people would start to do it
just
and they'll be
kinda
like,
solidify all that.
you're gonna waste time unless you notice. But yeah, if I said, if I did a problem like that, I'd say, discuss the issues with this question. Don't actually solve it or something. I have to do it.
Well, I'm just saying, like, just to
You know what I'm
simplify,
saying?
like, what.
Yeah, if that did show up on a test, and it said solve this around the point x equals 1, you'd have to realize, can't do it.
But that's why we say x equals 0, because, like, you wouldn't be able to at x.
Yeah, I could use anything else except 1.
Okay.
Yeah. Now, the section 6.3 does discuss finding solutions about singular points, certain types of singular points. But we didn't officially do 6.3. Yeah. So if you're at all curious about, are there some singular points I could actually find solutions around? Yes, there are.
I'm gonna do some light reading this summer.
Yeah, some beach reading. Yep. Work on your sign over cosine. No? Okay.
Oh, jeez.
Oh, jeez.
Oh, thanks. Just,
Mm. I
Doing
can't take
math
credit
over
for that.
here.
I can't take credit for that. It's all on a shirt somewhere.
Oh, I just got it.
Tangent, yeah.
There you go. Cool.
I thought it was just like that.
Let's
I
see.
took it at face value to begin with, but got it now.
Yeah, that's me on the beach. Sign. Expand that. What are you doing, mister? Get away. Mom, I swear. So now, this one tripped some of you guys up on the test. You weren't sure how to handle this, and this was showing up. You can't have your CNs being based on X, because then they're not really constants, right? They're based on the value of X, which means they're functions of X, and that's no good. So that tells you something went wrong. If you need to, you can write for yourself X. You can just, before you do anything, distribute that. So you see what you really got here. You have 3 series, right? So if you do this first dude, bring that X in. And then you get the normal thing. Plus that. All right, and This next step should be, when I first got into these series solutions, the very first thing we did after a brief review was to really hammer home the two things you need to do.
There's your X of n, then your
Yeah,
index.
exactly. Get your like terms to start first, because then it's easy to just take the terms out until the indices match. So the only one that's not like terms at the moment is this one. I could base everything on n minus 1. There's really nothing wrong with that.
Mm-hmm.
Or you could make everybody x to the n. What do you guys want to do?
Everything X to the end.
Everything x to the n. Okay.
Yes.
I like it. So then, go ahead and write down what these would be. Shifted, x to the n. And if you use k, that's fine. I'm not against that. I think computer programmers would not want to use it the way I do it. Let n equal n plus 1.
Yeah.
Oh, shoot. I really only have one marker. Oh, well. So what's this first guy become? N equals what? So what? What's infinity of n equals? Oh, you guys are still working, so. All right, guys. What's this first one become?
N equals 1.
I like it.
C
So then,
plus 1.
Yeah.
N times n plus 1.
I like it. I like it.
X to the n.
Good.
N equals 0. C n plus 2. N plus 2. C. N equals 0.
Yep.
C n plus 1. N plus 1.
And you can do checks and balances. Once you do something, you can make sure that when you plug a 2 in, it gets C2, 2 times 1. And then when you plug a 0 in, you get C2, 2 times 1. And you can just double check and make sure that the first term matches after you do the shift. And now, what's the one thing you got to do for the next level?
Change your indexes.
Yep. So, who needs...
Drop your first one to 0. Or no, raise
See,
it.
that would require you to go,
And that's what
like,
you
back
say.
in time or
Take
something.
one out of the zeros.
So,
So yeah, you can shuck some stuff off of those. Yeah, so for n equals 0, you get, you get 2 times 1. You get 2c2 x to the 0. I'm just going to put it over there because now I can just basically put everybody together, right? Except for the last guy. What do you get for the last guy needs help too. What's the last guy's n equals 0?
C1.
Good. x to the 0, which is 1. I like it. Now I can do, let's see, Cn plus 1, n plus 1, times n, minus Cn plus 2, n plus 2, n plus 1, plus Cn plus 1, times n plus 1, factor out x to the n. Okay. So I think most of you guys have the process down pretty good. You just get lost in some details, which, you know, on balance is the better way to have a mistake. What can you see right now off the bat? Yeah, so you can do two things right now. You could set up the recursion relation, and you can see the relationship between C1 and C2, right?
C2 is 2 times C1.
C1 is 2, C2.
Yeah, C1 is 2C2, so C2 is 1/2 C1. And then the recursion relation. So I solve for the bigger one. You see how these both have Cn plus 1 in them? Right on them. And see how this is negative, right? Let me see if you guys are cool with this. So I'm gonna like take this term over to the other side, so that these stay equal. These stay positive. Some of you guys just weren't careful about moving stuff over. You sort of like moved over, like they teleported over. No, you got to subtract or add them over, right? And here I can take a Cn plus 1 out. And let's see. And what's funny is, let's see if you guys are cool with this. See how I can take a Cn plus 1 out and out of these terms here. What else I got to take out?
N plus 1.
N plus 1. Become a plus 1. And then what's left?
Cn plus
N. I took a Cn plus 1 out. I took an N plus 1 out. So what's left? N
1.
plus 1. So I just get N plus 1 squared. Yay. There's something like that happened on the test. And it would still work, obviously, if you don't reduce it, but shit, I'm going to reduce it so I got less stuff to plug in, right? And now I can divide and stuff cancels. That's nice. You always solve for the higher index one. And then you get n plus 1. One of those cancels times Cn plus 1. So here's my relationship between coefficients. And where am I going to start? Looks like n equals 1. Because I know C0 and C1. I always know those. And what's C2? 1/2 C1. So I know C1, C2, I know C0, C1, C2. And if I start where this guy says to start, I'm going to get C3. Kick ass. That makes beautiful sense. So C3, so if n is 1, I get C3 is
over 3.
2/3
C2
C2, and of course C2 is
is half C1.
half of C1, so I get C1 over 3. Let me stop here for a second. See? You guys cool with it so far? The steps don't change, just the stuff. Replace these with the series stuff. Get your like terms, get your indices to match. Deal with any of these things. Set up your recursion relation, and then just start getting constants. Did I leave somebody out? Good.
How do you know you have C naught and C1?
You always do. Those are the two things that are the true constants. They're the ones they're going to be the ones that have values based on the initial conditions. Just like C1, C2, like yc equals C1 e to the t plus C2 e to the negative t or something. What is C1 and C2? Well, whatever they have to be to make them match the initial conditions.
Okay.
So C0 and C1 are the real constants that every other supposed constant is based on. So they're they're only two, I would call it a parameter at that point, because that's controlled in a lot of different ways. Is that, it's sort of like the Fibonacci sequence. You got to start with 1, 1, so you can build to make 2. I got to start with 2 seed values to build all the other values. So now I've got, so this is C0, C1, C2, C3, is C1 over 3. Now what do you notice here? What's going to keep happening? Are we able to notice this yet? If n is 2, what do you get? C4 is? C3, and C3 is C1 over 3, so you get C1 over 4, right? Is that cool? Is C0 ever going to show up again? It's not. And where's the only place Z0 shows up? It's the constant term. And why does it make sense? There's no y here. What's automatically going to work then? Any constant value is going to be a solution. That's what that's saying. Do you guys see that? Any constant value automatically is a solution because there's no y term. So one of the series is just C0. All right, that's done. All right. All right. Instead of going forever, it's just the constant. It's beautiful. Whenever something weird happens, like there's one of the tests, you should have gotten one of the two was just a 2-term polynomial deal. And that was it. And if you look back at the original equation, if you plug that in, it works directly. It's beautiful. So it's kind of neat when that kind of happens naturally. You get a nice little short answer. The other answer is kind of more involved. But I'll bet you anything. What do you think this is going to be? Let's see if it is. 4 over 5, C4. C4 is C1 over 4, so sure enough, this is C1 over 5. Is that cool? All right. So that's enough to really build up a pattern. So one solution is C0. And the other solution will be C1 times 1 over 1 plus 1 over 2 plus 1 over 3, right? Oh, yeah, my x's. I forget my x's, yeah. 1 over 1 times x. 1 over 2 times x squared. That's beautiful. So how do you write the nth term? 1 over n.
To the x to the n.
X to the n plus 1. And the nth term for this series I'm talking about, like this is the first term for this series. Are you guys cool with that?
Why'd you do x to the n plus 1?
Why did I do x to the n plus 1? I don't know. Just because.
I was a little scared.
You should be.
Do we need to include that? Do we have to include
No,
that?
no, that's fine. No. Only if I ask you to, right? I mean, we remember how difficult it can be sometimes to see the pattern. This pattern is like, oh, okay, that's awesome. Okay. So the important thing with any example problem is to make sure you understand the steps. Why are the steps what they are? And I can always apply them. Yes, of course you can. Okay. Yeah.
QF. We do that one on the doctor final.
I'll give myself a copy. Give all of them away. What does it 2n say? I gave all mine away.
Do we need a copy?
Yeah. Two, which one?
F?
2F. Okay. Ah, Bernoulli's.
Oh, yeah.
So everybody got what they want from this guy? Okay. I like the way I put that too. All right. And you know, for right now, just to remind yourself, you can look at the little outline, because Bernoulli's is right there in chapter 2. So if you look at the form it should be in, you can already identify what n is. Right? There's no y thing that I have to divide by, so you can already see what n is. And n is related to the thing that's keeping it from being linear. This is almost linear, except, of course, for the stupid flesh.
Why?
Y cubed, right? If this was y to the first, why would that not be an issue? Because I could just suck it into this dude. Because I can have a y right there, no worries, right? So if it was y to the 0, that's definitely no problem. If it was y to the first, I could just put it together with this guy. So that's why 0 and 1 don't really come into play for Bernoulli's. You don't need it. So if you want to, what would you do to really make this in the right form
Divide by
in general?
x squared.
Yeah, divide by x squared. Now what do you guys notice?
Same power.
Oh.
Yeah, it could also be homogeneous, and I just chose to force you to do Bernoulli's. Let me see. Oh yeah, I gave it back to you. Okay, so what is n?
Is y
3.
It's 3. And then the substitution I make,
Y equals 1
n
minus
minus 1.
1 minus
Plus
3,
one or n
or
minus
u
2?
equals
u equals y to the
1
1
minus
minus 3.
1 minus n. So u equals y to the negative 2. Now here's where somebody happened to ask me this earlier and made this mistake. I'm not picking on you because this happens all the time. I can't even remember who it was. You got to be careful when you solve for y if you want to do it that way. What do you have to do to both sides to kill that negative 2 power? You got to apply a what power?
Negative half.
Negative half. You can't just move the negative 2 over. You can't do anything freaky. So y would be u to the negative 1 half. Because then I can just directly figure out what dy dx is. So what would y prime be?
Is EF half u minus 1, so it's going to be
So minus 3 halves. 3 halves. D, U, D, F.
I think normally you do the dy dx notation for this, but it doesn't really matter. The prime is set up as per dx, yeah. Okay, so now you make that substitution. So now you get, let's see, negative 1 half, u to the negative 3 halves, u prime, plus negative 1 half, u negative 3 halves, x to the negative 1, sure, why not? Oops, what you got out of there, Jeff? Y, just y. U to the negative 1 half, x to the negative 1. Equals, what's y cubed? So y is this guy. I just looked there accidentally.
U to the negative 3 halves.
Yeah, u to the negative 3 halves, x to the negative 3. You'll notice, I mean, if you do enough of these, this and this will be the same, which is what the substitution is built to do, so that it can go forward. So that this guy's problem was the dependent variable showed up here with too big of a power. So now the dependent variable is not going to show up here at all. That's what that substitution does. So now I can multiply everything by what? Yeah, negative 2. And actually, well, I mean, now you could do that. Which way do you want to go forward with this? What does this substitution do to the equation?
multiply with what get rid of u, the term of u.
Yes.
So you divide everything by u to the 3 over 2.
Okay, so I like. Well, what's this guy's goal? What's it supposed to do to it?
It becomes an integrated.
It becomes linear. So you can apply the integrators, because that's what it almost was to begin with. So this is going to try to make it linear. So if I just solve for u prime like we did in the first place, We wanted this to be linear. Shit, we did this substitution. We get this weird shit. Now we solve for u prime again because we want it to be linear. That's the whole purpose. So if I multiply by negative 2 u to the 3/2, right? Because dividing by that shit is just multiplying by the reciprocal. All the way across, Jeff. Boop. And then the same thing on this side. Negative 2 u to negative 3/2. Positive, sorry. Then we get, here of course this cancels, that's the whole reason we did that.
U prime plus minus
Minus.
Q. U half. Oh,
Oh, yeah.
Yeah, because 3/2 minus 1/2
Oh,
is 2/2. Nice whole u. Sorry, sound like the counseling section. We're trying to make a whole u.
negative 2x to negative 3.
Yeah, negative 2x to negative 3, I like it. So negative 2 over x cubed, however you want to write it. Just stop for a second. So it's, I mean, this is a perfect class to realize what math is really all about. There's nuts and bolts steps, and then there's ideas. Not just behind every step, but also behind the goal. Why did we even create these steps? So that's why I was trying to make sure, not only should you know what the steps are, but you should know what the goal of it is. Because if right here I still added u squared or something over here, that's trying to tell you you did something wrong. You did something wrong here, or you chose, or n was wrong, something. I like it, because if there would have been like another y here, then you just didn't divide by enough to see what n really was. I mean, that's okay. So now what do I do?
Integrate factor.
Integrating factor. I love it. So you guys try to finish this up. So what is p of x?
Negative 2 over x.
Negative 2 over x. So you guys, if you do enough of this, you kind of know where that's going to go. It's a beautiful natural log. You can kind of see it down to negative 2. So you want to do e to the integral.
Of negative 2 over x.
Which of course is e to the negative 2 ln of x. The negative 2 goes up on the x. The e and the ln kill each other, so you end up with x to the negative 2. So if it was negative 3 over x, it'd be x to the negative 3 straight. All right, and of course, what do I do with that?
plug it back, or
Multiply by equation.
multiply
You multiply everything by it. I love it. That's why I love the idea of integrating factor. Factor implies multiplication. So something to multiply by to make it integrable. So the shortcut on this is going to be what? Now, if you do the shortcut, you got to remember you're actually multiplying by something. So it might be a good idea not to just go straight to what it's going to be, but actually apply this. So let me, it doesn't matter, Jeff. Minus 2u over x cubed. I got a mixture of stuff, but who cares? So now I'm just basically dividing everything by x squared. And the reason you want to do this instead of just going straight from here to D blah is because sometimes you guys forget to actually give this guy the integrating factor. So what does this become?
X to the minus 2u.
Yes, x to the negative 2u. Integrating factor, u. I love that. That's too good to believe. Equals this, and then, of course, what was underneath here would be dx, so that goes over there. Integrate both sides. Okay, okay. Is this coming back? So I'll do this side. It's funny every time, Jeff.
Never gets old, right?
If you know what's good for you.
That one was new. Nice.
When you integrate this, what do you get? So if you write this as negative 2x to the negative fifth, x goes to become negative fourth, goes up by 1, right? So you got to divide by negative 4. So negative 2 divided by negative 4, 1/2. I like it. Is that cool? And you can always quickly check yourself. Negative 4 comes down, divided by 2 is negative 2, x to negative 5, yay! Just make sure the derivative actually works back, right? And another big thing is, you guys, I understand that there's sometimes we don't write plus c and there's sometimes we do, and it gets a little wonky, but here is definitely a step you need the plus c. Might as well just call it plus c1. Now what started this whole thing off?
U equals
The u substitution.
Yeah, so we had this u substitution, so I mean, so once we get what u is, so if I multiply by x squared, this becomes 1/2 x to the negative 2 plus c1 x squared. And of course u was
Y to the minus 2.
y to the negative 2. I love it. So then you just get, so just to cut down on writing, is this cool? I'm going to make it y squared equals 1 over that.
Wait, why is C1 x to the 2 or x squared?
And multiply by x squared to kill this x negative 2.
Oh,
So multiply both sides by x squared to kill this. So that becomes 2 more x's, and that becomes 2 more x's back. You know, you can mess with this thing a bit. 1/2 x to the negative 2. Hopefully I got you guys to the point where you won't take that square root. Because then you got to introduce plus or minus. It's just messy and unnecessary. One little thing I could do with this is to multiply by 2x squared on the top and bottom. What do you get there? You can do it. 1 plus c2 x to the 4th. And that just looks a little bit cleaner. I think on the answer key, did I actually... No, thank God. Yay.
it seems simple now, like going back.
Well, I mean, yeah, once you've gone through chapter 4 and you go back to 2 and you're like, I don't remember any of it. Wait a minute. Oh, yeah. Okay. Not that bad. Compared to some of the other stuff we've done.
Yeah.
Yeah.
Like, there's a lot of integrating, but like the steps are, there's like 3 major steps.
Yeah, exactly. And integrating factors we used every now and again, so it should still be in your head decent. Bernoulli's, we haven't seen that shit since chapter 2. Yeah.
Euler's was the x to the m function.
Oh, Cauchy-Euler, yeah.
Yeah.
X to the m, yeah.
Can we do number 5?
Oh, yeah, okay. Ooh. All right, let me see.
I don't know if I want to do 5 now.
No, I just haven't worked it out since last semester, so
Oh.
it looks neat. Now, ooh is more like, ooh, it looks neat. So we got this, oh, you guys all got this. It's all
You're the
good.
one that gets stuck in a math problem in a restaurant, folks over a napkin and starts to work on a napkin.
Yeah, I
aren't
can't
you?
let it go.
What is that?
We did 5, I thought, last time, because that was the
No.
reduction order, wasn't it?
Well, we didn't do it. I think we talked about it. Or did we do it?
I only said it because I wrote order of reduction next to it.
No, we talked about it. I'm pretty sure we didn't do it.
Oh. Is that reduction right? What?
All right. So I didn't say the phrase of the
Oh,
method.
yeah, I remember doing this.
We did it?
Yeah, we did.
Yeah,
Oh,
I
okay.
just didn't realize that it was just saying reduction.
All right. But what, just realize the key part of that that tells you to do this method
He gave us
is
one.
I gave you one and asked you to find a second linearly independent one. And if you just look at this DE by itself, I think, yeah, that's right, we talked about this. We said,
Yeah, we did.
well, if I just gave you this and said solve it, what's the only method you could really use?
Power.
If you didn't know this, whoop,
Serious.
you have to use series, yeah. And that would be fun.
The only question on the test.
Yeah, the other answer, gosh, that's horrible. I really don't remember doing it. Which one was it? 5?
Yeah,
We didn't
I think
finish?
I think this is the one that got gross. We didn't finish.
Yeah.
We went it's gross.
No.
No, it didn't.
2E was the gross one. 2E was the one that you couldn't really go forward.
Yeah.
5, I think I just said, and the
We
rest
stopped
is
it.
pretty straightforward.
We stopped at where
The answer is much nicer than you would think if you look at the answer key.
we do 7 in that case.
7?
Yeah.
Oh, fun.
Oh, yeah, okay. All right.
Oh, so
Um,
that's why it's just an equation.
I mean, I think there's a example almost exactly like this.
That's me.
It's recognizing this way function.
It's like dueling set brackets here. Okay. And of course, definitional plots is based on integration. Integrals can handle piecewise defined functions. So you just have to apply the integral to this. So I mean, what is this in general?
It's e to the negative st.
Yeah. So what you end up with is that function is defined on 2 different domains, so you end up with 2 integrals based on those regions.
Yeah. And then you'd have to test the points.
So it'd be from 0 to 3, e negative st times 2. And it depends on how you want to do it. Minus integral from 3 to infinity to you have to fight against the urge to combine those somehow because they have different limits, very different limits. I mean, the definition is just integral. Integrals can handle piecewise, easy. So you just apply that definition to it, and I just evaluate both of these intervals. There's no infinity here, so you're going to get, you're not going to have anything go away, right? So what do you when you integrate this?
2 over -5.
Or, not that far ahead, sorry.
So 5.
No, I think he's talking
Oh,
about the
sorry.
answer. Yeah, maybe, I don't know. So you get, when you integrate this,
2 over negative s.
you get 2e negative st over negative s.
Oh, evaluated from 0 to 3.
Plus. Just straight line on top.
Minus.
Should be plus, shouldn't it?
Where's plus?
It becomes a plus. It becomes a plus.
Yeah, it becomes a plus eventually because of this guy. I like it. So, I mean, these are the same.
Oh, wait, do you subtract these 2 integrals from each other?
No,
Oh, because
It's just because of this. It's just because
Oh,
of
okay,
this.
I brought my, I
Is
did
that cool?
plus and I kept my negative on the inside.
Sure, I love it.
I see what you're saying.
I'm with you. But it will become a plus eventually, because this would be
Yeah.
negative 2 e to the negative st over, so it's 2 e to the negative st over s from 3 to infinity. What's up, guys?
Like N3?
Say again?
Like N3?
Yeah, now you just start plugging stuff in.
So with the infinity, it would be 0, right? Because it'd be on the bottom.
Right, so if you want to look at this guy, yeah, this guy first. When you plug a really big number in here, it's going to be
Is there?
2 over a really big number.
Okay.
Yeah.
Yeah, and s here is just a constant, right? Yep. So that's 0 minus, when you plug a 3 in for t,
2e negative s3 over s.
all right, I like it. And then this one, when you plug a 3 in,
2e negative s3 over negative s.
and when you plug a 0 in, you get, so minus a negative, right?
Yeah.
This is 1, so it'll be 2 over s. So you get 2 over s minus 4e negative 3s over s.
You just combine the terms.
Yeah, there's negative 2 business minus 2 more business
Adding
Wait,
together.
how did
equals,
Adding together.
What happened when you evaluated those? Oh, 3.
Yeah,
Okay.
together.
Oh,
plug a 3 in, and then minus plug a 0 in, so minus 2 over negative s is plus 2 over s. Now of course, this is almost the function 2, right? And what's the Laplacian of 2?
1 over s.
2 over s.
Yeah.
Minus an adjustment because of the
Of where it's at, yeah.
piecewise nature. Okay, maybe. That one isn't hard. It isn't. It's just the definition of Laplace is a
Integral.
nice integral. You know, based on what the function is, but you can't beat a freaking constant function. It just kind of changes which constant it is, right?
Maybe the only hard part is a partial fraction.
This is not a plane you want to be in. 2, negative 2, you're all dead. It's a rough day. It's been a rough day.
What was
Yes.
the wrong scheme?
So you use variation of parameters when you have two solutions already?
Yes.
It's like in place of.
And those 2 solutions come from, when you use variation of parameters, where do the 2 solutions that you use come from?
From the powers of
Yeah, so auxiliary.
Yes, it's the C, it's the complementary, right? So you get those 2, and then you build a set of solutions using those 2. I like it. Yes?
What was the wrong scheme used for again?
Variation terms.
Was it?
And I don't think I ever said this, but reduction of order is based on the fact that the 2 solutions have to be linearly independent.
Yeah.
If I get yc equals c1 e to the x plus c2 e to the 5x, and I have a dE equal to e to the 5x, is the solution going to be some constant times e to the 5x? No, it's going to be x e to the 5x plus who knows what else, right? So what variation of parameters does is it says, okay, if I know 2 solutions that make it 0, my yp has to be linearly independent from both of those. So it just takes reduction of order up to the next level. I like it. Okay. Of course, I cheated a little bit and had a computer do that for me. I figured it'd be nice for you guys to, for once, really understand what it was I was writing by just not being the one to write it.
No, actually, that's not the first time I've used computers, because all 3 of them made us do it too. 'Cause
Oh, hell
some of
yeah.
the graphs get really gross to hand draw.
Yeah. So imagine back when we didn't have that
Unless you're like me,
capability.
you get smart and make it easy by rotating something to zero, you're getting yelled at for altering how the graph looks. You want the volume under those weird shapes, volume doesn't change.
So it shouldn't be any problem.
Yeah, you maybe do like redo one of the tests, because it did that for like every problem, it's like Z's gross, every time it was like, well, like, when they call the cosh function, it makes it all pretty. You know, x squared being 0 is.
And only if you said don't do that, then that's a
But I
problem.
only have to figure out one gross part. Hey, what was the right answer? Is there anything that you don't have on email?
I'm not sure. It's an interesting question. Yeah.
For the first one, can you go over what it means for A to be autonomous? I just-
Yeah, autonomous is related to phase portraits. Because that means that,
Oh, yeah, it's gonna be the same thing.
because remember, I never want you to forget, when you have especially a first order DE, it's easy to see this, but it's basically a slope function then, right? So if I had this, I could actually graph the slope field. And that's part of what chapter 1, I think, was. So if I don't have x dependence, that means that the slope only depends on the y, which means I only have to do it once, because as I move along the x-axis, it just repeats itself. It doesn't give a shit about where I am on the x-axis. It only cares about where I am on the y-axis. That's why I can do a phased portrait with a single line. So autonomous just means that the dependent variable is the only thing that the slope depends on. So the first one, it was a bunch of stuff, but it only had y's in it, so it's autonomous.
It doesn't have the Z's.
Now, there might be some stuff I missed. I don't know. Anybody got more than what I wrote down there for 1A, B, C?
See, that's what I was trying to think of. I was like,
Is that what you're trying to think of?
yeah.
If I could read students' minds, oh my God. That would be amazing.
I know who would fill right off the bat.
That'd be hilarious.
Already gave him a grade.
You get a B, you get a C, you get a D. What the hell? What are you thinking
I
about?
don't know, I'd go both ways, because you find that like the A students that aren't studying are doing it. And then I've had people like that, best friend, girlfriend at the time, math major, hadn't gone to any of her classes, freaking out about her final. I'm like, you got an A, like you could like 0 this final and still pass.
If you do another matrix problem, that'd be pretty cool. Good idea.
Oh yeah, we did that, the one on there
I mean,
last
just
time,
a
right?
different one or.
Let's see.
Something randomly generated.
That you did
Pretty gnarly.
No, actually.
I've learned by repeated example not to do that.
7.65.
Oh, let's see. Yeah, let's try this one. I'd only give you one of this level.
You do turn an 18 into, hey,
A1, A2, yeah. Those are due on the day of the final.
Okay.
I saw a teacher teaching this, that you would solve this for like x, plug it in, then take the derivative, plug that in. That would be horrendous. Sorry, is that the if that's you, you should really stop doing that. Yes. That would work. Oh my God, that would be horrible. So how do I rewrite this first guy?
-4 minus, oh,
The x
We could do it. D.
Oh, we're not doing this?
Oh, I thought this was a matrix.
So did I was.
Oh, it is a matrix. I'm sorry. You're right.
Thoroughly confused for a moment.
I forgot what the request was, and I just started attempting it like 4-9. All right. So how do you rewrite this?
Negative.
What's A? Let's identify